morning, and welcome to Virtual Class 14. Today is Tuesday, May 19th. We have just one short segment for today's class where we combine the ideas of entropy and free energy that we learned about last week into a simple problem that we're going to work together. We're actually going to do the first homework problem together. And then on Thursday of this week, we'll have a lab exercise on the energy associated with food, calories, and so on. So we'll do that activity on Thursday, and there'll be a short video to accompany that as well. I hope everyone had a great weekend. Looking forward to another very productive week. So without further ado, I'm going to send it out to Kevin, who's going to go over that sample problem involving free energy and entropy. Take it away, Kevin.
Thanks, Kevin. Okay, what we're going to do today is we are going to go over the same three homework problems that we had from the enthalpy exercise on Thursday of last week, but this time we're going to be looking at entropy and free energy. So what I've decided to do, because today's assignment is a little longer, is to do one of those homework problems with you together as you watch the video. So please make sure you write this down. You still need to show work for it in order to earn full credit for the homework, but I wanted to go over one of those problems together to kind of lessen the load for tonight. All right. If you look at the problem, we're going to choose problem number 1, where we have the combustion of propane. So we have propane reacting with oxygen, producing carbon dioxide and water. Last week, on Thursday, we found out that the delta H for this reaction at standard conditions was equal to negative 2,220 kilojoules per mole. If you don't recall, or if you're watching this without having watched the previous video, please go back and watch Virtual Class 13 to see how we came up with that value. Today, we're going to be looking at delta G and delta S. So for delta G values, we're now going to be using the middle column on the thermodynamic data table that I published last week in the materials folder. So I'm going to go through those calculations and I'll remind you of a few important things along the way. So for delta G, at standard conditions for the reaction, we have, remember I enclosed the product side, because we start with the products, enclose the product side in square brackets and each of the individual values in regular parentheses. So the value for carbon dioxide as a gas, the delta G value for this is negative 394.4 kilojoules per mole. We're going to multiply that by 3 because of the 3 in the balanced equation. I'm going to add to that the value for water as a liquid, so negative 237.13 kilojoules per mole. I'm going to multiply that by 4 because of the 4 in the balanced equation. A reminder that states of matter are important. They have different values depending on whether you look up a molecule as a liquid or a gas or an aqueous form, depending on what it is. So be extremely careful. That is the number one mistake as we are going through this, which is choosing the wrong value. So now I'm going to subtract my reactant side. So my first value is going to be the value for propane, which is negative 23.47 kilojoules per mole. I'm going to multiply that just by 1. Plus the value for oxygen. Now the free energy value, just like the delta H value, for an element in their natural state is 0. So this is going to be 0 times 5. Doesn't really matter because this still ends up being 0. So when we perform this calculation, we're going to get a delta G value. So that's this right here. A delta G value for this reaction that is equal to negative 2,108 kilojoules per mole. Now, for delta H being negative, that meant we had a reaction that was exothermic. Heat is given off. For delta G being negative, that means we have a reaction that is spontaneous. So if you think about the energy diagrams, once we get over that activation energy barrier, this reaction is going to go. So there's no question, obviously we know this from our own experience, but propane combustion of it is a spontaneous reaction. So let's go back now and calculate the entropy associated with this reaction.
So I'm going to look at the S values at standard conditions. So the first one, the value for, remember we start on the product side, so carbon dioxide, the value is 213.6. Notice the unit is different, joules per Kelvin mole. And we're going to multiply that by 3, plus the value for water as a liquid. The value for water as a liquid is 69.91 joules per Kelvin mole. And we're going to multiply that by 4. From that, we're going to subtract our two reactants. So the value for propane, which is 269.9 joules per Kelvin mole. We're going to multiply that by 1, plus the value for oxygen. And now, because we're talking about entropy and not enthalpy or free energy, the value is not 0. So in this case, the value for entropy is 205.0 joules per Kelvin mole. And we're going to multiply that by 5. So when we do this, we get a value for delta S for this reaction that is equal to negative 374.46 joules per Kelvin mole. Now, remember what a negative value for delta S means. That actually means it's becoming more ordered, more organized. Now, if we look at the states of matter, we'll see why that makes sense. We have 1 plus 5, 6 moles of gas becoming 3 moles of gas and 4 moles of a liquid. Well, going off of what we talked about last week, gases are the most disorganized. So below that is a liquid. A liquid is actually more organized. So this is decreasing in entropy, decreasing in entropy. So it's becoming more ordered because it's forming this liquid. Okay, so if we put all of this together, we have this equation, and this equation is at the top of today's assignment, and it was on the board last week. So delta G for a reaction is equal to delta H for a reaction minus T delta S for a reaction. So let's put all this together. We have delta G for the reaction. We calculated that part today. So that's negative 2,108 kilojoules per mole. And we're going to set that equal to delta H for the reaction. This is the value that we calculated last week. Negative 2,220 kilojoules per mole minus the temperature, 298.15 Kelvin, times, now notice that delta H and delta G are in kilojoules per mole, but delta S is in joules. So before we can plug it into this equation, we have to divide this by 1,000 to get kilojoules. So negative 374.46 is going to become negative 0.37446 kilojoules per Kelvin mole. This will not work out unless you convert that, so just be mindful of that. So now I'm going to have negative 0.37446 kilojoules per Kelvin mole. And notice how nicely, because we're multiplying the value for delta S by our temperature, the Kelvin here and the Kelvin here drop out. So this overall term has a unit of kilojoules per mole, which allows us to add and subtract. So when we type that into the calculator, we wind up getting our very same delta G value, which is good, because that means we did everything correctly. So what I did, and you'll see this when you look at the answer key, is next to it, when it does work out the way it's supposed to be, I just write a note here that says verified correct answer. So what I would like you to do tonight for homework is to practice this with the remaining 2 problems. So for each of the problems, you're going to calculate a delta G value a delta S value, you're going to use this equation to show that it verifies. Now, I do want to caution you on one thing. There is a typo in the data, and I found this out the hard way after I did the answer sheet and I could not get my values to work out. So when you're looking at the value, the entropy value for iron 2 plus, the value should be negative 113.4 joules per Kelvin mole. It's not common to have negative values, which is probably why it was left out inadvertently. So the value is negative 113.4 joules per Kelvin mole. I put a note at the end of the answer sheet on this assignment, but I'm going to just mention it right now. The way I found out is because when I tried it using the number provided, it didn't work out. So then I went to a new source on the internet to try and verify all of the individual values for both delta G, delta H, and delta S to try and figure out why my answer wasn't working. And that's when I came across that the value for this is actually supposed to be a negative number. All right, that is it for today. A very short lesson. Again, on Thursday, we're going to have our lab. I'm going to send it back over to the desk for Kevin, who's going to sign off for today. Thanks very much. Have a great week, guys. Thank you, Kevin. So that wraps it up for today's class. A reminder that you should do homework problems 2 and 3 in the exact same fashion that I just showed you. And that on Thursday, we'll have our food burning lab, and there'll be a new short video to accompany that lab, and you can see not only an example of that, but what the calculation is going to look like. So I will see everyone on Thursday. If you have any questions, please email me or send me a message through Schoology, or better yet, drop in on one of the 2 Zoom sessions today at 10 a.m. and 12 p.m. Thanks very much.